Okay, let's move on to the second part of our lecture. So here's a question then. If the rebelling teenager or the transforming epithelial cell is becoming more and more sort of messed up, so to speak, and the implication is eventually, if we're talking about this transforming cell really becoming full-blown cancer, then it must imply that the transformed cell must get to a point where it's manipulated the stroma to such an extent that the cell can now break free of the limitations of the basement membrane and begin to actually spread beyond the original in situ site. So these communications then that are happening between the epithelial cell and the stroma, are these newly invented novel ways that the epithelial cell kind of comes up with that the stroma has never seen before? Just like, is it the orchestra that gets crashed by the rock guitarist? Or is it more a matter of the transforming epithelial cell making use of existing physiological cellular pathways that maybe are already in place, but have just not been activated? And so I think all of you know the answer to this. And that is, just as the transformation of the cell itself involved deregulation of existing pathways within the cell, so do the events that allow the tumor cell to alter the extracellular microenvironment. So it's not as though cancer is inventing something new to trick or manipulate the stroma. It just is somehow activating a set of different signals that represent or result in the stroma being confused, manipulated, and ultimately helping the tumor cell. So in other words, the tumor cells must trick the surrounding tissue in order to help and support the tumor, the growing tumor, to thrive, expand, and ultimately invade. So one way to think about the timing of this is that we said that the deregulation of all the little pathways inside the transforming cell itself took a very long time, many years and many generations, in order for the right set of mutations, random mutations, to be stumbled upon by the transforming cell, right? 10, 15, 20 years plus. But now that the tumor has actually reached a point where it's big and it is ready to kind of spread, right? You have to imagine that it's reached a point where it needs to trick the surrounding stroma pretty quickly, because it's running into all kinds of problems, limitations of it becoming so big. So it's not going to take 10, 15 plus years. At this point, it's going to be something very fast. So therefore, it must be that there is a whole set of different pathways that already exist that just get activated as though it's an on and off switch. And that's what then quickly allows this next step of the tumor to invade the surrounding tissue to happen. So if you think about this for a moment, what types or what set of pre-programmed pathways might there be that have evolved so that they are a program that's ready to go at a moment's notice in order to do something that encourages epithelial cells to grow, spread, move around? Can anybody think of a situation where you might need to, in an emergency, kind of get your epithelial cells growing, dividing, and moving around?
If you have like a cut or something?
Yeah, right? So tumor formation then has many parallels with wound healing. And this is something that really we've begun to appreciate only in the last decade or so. This was something that was really overlooked before. The idea is wound healing is a situation where you have an emergency. You have damaged tissue, you're losing blood, you need to quickly activate a whole program that evolutionarily we have ready to go in order to mobilize different types of cells, in order to move cells around, in order to stimulate blood vessels to grow. and importantly, to also mobilize things like our immune cells. So let's take a look at this figure here. So this is a flow chart that doesn't necessarily have to do with cancer, but is really the flow chart of wound healing. And we can think about wound healing programs being a whole bunch of different cellular signaling events and cells themselves being recruited and activated to do things to the stroma, as well as do things to epithelial cells. So for example, if you have a cut, right, you're going to have damage to your vasculature. Your blood vessels are going to be ruptured. And that means things like plasma from your blood will seep into the surrounding stromal tissues. So this word here, parenchyma, if you see it, it refers, it's sort of a general term. It just means the stromal parts of tissues in organs. Okay. So normally the stroma would not be exposed to plasma. You would also have things like platelets beginning to aggregate or clumping to help things like clotting. And platelets would be degranulating, meaning platelets will be releasing different types of growth factors, like platelet-derived growth factor or TGF-beta. Okay. If we think about it, tumors can actually mimic this type of response. The tumor blood supply, the blood vessels that are going through the tumor are actually very leaky. They don't have good integrity. So here is an image of various capillaries that are stained bright red, flowing through healthy tissue. And you can see that the blood supply is very nicely contained in this network of capillaries. The blood doesn't actually seep out into the surrounding tissues. This is the blood supply of a tumor. So if you take a cross-section of a tumor and look at its blood supply, what you see is that the capillaries are very leaky. That means components of the blood, like plasma, are constantly leaking out. And that means many of the growth factors that are normally contained in the blood are also leaking out. So things that result in the release, for example, of lots of platelet-derived growth factor and TGF-beta. Right? And also, these will stimulate the release of many different types of vascular factors that try to encourage the formation of new blood vessels. So if we go below that, these growth factors end up stimulating macrophages. So macrophages are the main type of leukocyte or white blood cell that are sort of patrolling around inside of our solid tissues. They do things like attack pathogens or eat up, clean up damaged healthy cells. But they also can remodel the tissue to help support healing. Macrophages get recruited, as well as fibroblasts. Macrophages help remodel the stroma because they produce a set of enzymes known as MMPs, or matrix metalloproteinases. So the job of these MMPs is to essentially eat away the damaged tissue at the site of a cut, because obviously that damaged tissue needs to be cleaned out so that you can then have a nice cleaned up area where the new healthy tissue can be then encouraged to grow in and fill in the site of the damage. These macrophages and the fibroblasts also send out VEGFs, or vascular endothelial growth factors. So growth factors that specifically stimulate the growth of new capillaries to come and begin invading the site of the wound to make up for the damaged capillaries that have been removed. So this table here is an example of some of these MMP type enzymes that macrophages that are recruited to the site of a wound employ. So these different MMPs digest different types of proteins that are normally part of the stroma. So collagens get digested, different types of proteins like gelatinases. They go ahead and actually clean up and dissolve the existing stroma to make way for new healthy tissue to grow in. So you don't have to memorize these but be familiar with this idea that these are different types of enzymes that macrophages that have been recruited to the site of a wound would use to clean up the damaged tissues. What about the VEGFs? We said that the macrophages and the activated fibroblasts in a wound release these vascular endothelial growth factors. So these VEGFs, they result in stimulation of new capillaries to grow, new lymph ducts to grow into the area. They encourage the migration of white blood cells that are circulating in the blood, such as monocytes, to actually leave the blood and enter the tissue and become things like macrophages. They stimulate your body to produce more of these blood cells, so hematopoiesis happens, and they recruit different immature hematopoietic cells that are growing in your bone marrow to actually come and take part in the healing of the wound. They also carefully regulate the endothelial cells. So these are the cells that are going to become the inner lining of the newly formed blood vessels. And they help regulate the permeability or the leakiness of capillaries that are in the area. So these are all properties of these VEGFs that get released. So if we look down at the flow chart here, ultimately then, the release of these different types of matrix metalloproteinases ends up digesting or eating away the stromal tissue. And remember, included in here are things like the basement membrane, right? The basement membrane that has been holding on to many of these other growth factors that were released by the stroma, preventing these growth factors from getting through the basement membrane and actually arriving at epithelial cells. So you're going to have a lot of release or liberation of growth factors that were trapped in the stroma. And then, of course, this is also going to lead to the process of angiogenesis, which is the term given to the stimulation of brand new blood vessels. So this will lead to new capillaries. And then the capillaries will be supplying oxygen and nutrients. That together with this big boost of released growth factors that were trapped in the stroma, this stimulates then epithelial cell proliferation. So if we're still talking about a normal everyday scenario of wound healing, hopefully you can understand, yeah, you can see how all of these things are important for quickly mobilizing things like epithelial cells. So the epithelial cells themselves then, remember epithelial cells normally, the ones that were surrounding the area of the wound, they were just minding their own business. So they needed to be stuck to a basement membrane and they wanted to stay put. But now they need to be encouraged to proliferate and actually move. So that means these epithelial cells are encouraged then by these wound healing programs to morph or change into mesenchymal cells. So mesenchymal, we've talked about this term before early in the semester, but the mesenchyme is another kind of term very similar to parenchyma, right? In other words, these terms mesenchymal, parenchyma refer to the normal stroma. Specifically, cells that exist in the stroma and function within the stroma can be thought of as mesenchymal cells. So in order for these epithelial cells then to be able to move through the stroma, to be able to get to the wound and begin to populate the site of damage, these epithelial cells have to give up their epithelial properties and change or transform into mesenchymal-like cells. That way, so that's the process of EMT, right? So then these cells move into the wound site, they proliferate, and now you fill in the area of the wound. Very importantly, after they do this, they have to resume their normal epithelial cell behavior, right? So they transform through EMT to be able to become mesenchymal and move through the stroma and actually then proliferate and fill in the site of damaged tissue. But once they do that, they have to revert. So the opposite is mesenchymal back to epithelial transition, right? So MET, and then you've had your reconstructed epithelium. So really what we're talking about here is if all of this is normal wound healing And it's a whole set of programs that are switched on to happen very quickly because evolutionarily, obviously we needed that as a way of dealing with even something as small as a paper cut. You don't think about it, right? But even something as small as a paper cut, if it did not heal, you would eventually bleed out through the paper cut, right? Or you would have the invasion of pathogens in your body from just that paper cut. So what we're trying to say here is that tumors, in a way, are able to fool the surrounding stroma to turn on the wound healing program. So tumors behave, in a sense, like internal wounds that are always healing, that they never fully heal. And therefore, the tumor cells make use of this existing set of pathways to promote proliferation, vascularization, and motility of transformed cells. This is a very strange way of thinking about it, this idea that a tumor is actually viewed as your body as a wound that always needs to be dealt with, right? So your body is constantly trying to heal this wound, and so that means the wound healing program, all the stuff that's in the background here, right, is constantly activated. But the wound never heals, right? Because in reality, it's actually the cancer that's tricking the stroma into keeping these pathways active. And ironically, these pathways actually lead to the tumor cell now being able to very quickly expand, and the tumor will now begin to grow even faster. So this last slide is just an example of how some of the immune cells are actually being fooled to take part in this. So we said that macrophages, that are immune cells that are normally patrolling through our healthy tissues, become recruited to the tumor. And the macrophages, because again, they're taking part in this activated wound healing response, begin to do things like remodel the stroma, like releasing enzymes, these matrix metalloproteinases that digest the stroma around it, releasing the physical boundaries for the carcinoma cells to be able to expand, and also releasing all those nice growth factors that were being contained in the basement membrane. So these macrophages that are associated with tumors, we call them TAMs, or tumor-associated macrophages. So here you see in blue are the carcinoma cells. You can imagine that originally these carcinoma cells might have been kind of contained in a basement membrane. That's why you still sort of see them sort of looking like they're surrounding the inner lining of a duct. But now these TAMs, these macrophages, have been tricked to come over. So these brown stained cells are the TAMs, and they're releasing enzymes that are remodeling and digesting away the stroma, including the basement membrane. And you can see down here, the basement membrane has now been dissolved, and all of these epithelial cancer cells are now free to enter the stroma. So obviously at this point, these epithelial cells have undergone EMT, because these cells clearly no longer depend upon being stuck to a basement membrane.